Transient analysis using Laplace transform. So we're going to do some maths we ain't done before. You're going to love it. Learn at outcome 4. Use Laplace transform to model transient response with RC, RL, and RLC networks. So Laplace transforms, they're a mathematical method similar to calculus. There is an alternative method of solving differential equations. In electrical engineering, it's often necessary to analyse the response of a circuit during a transient period, i.e. switch on, switch off. The simplest thing we know of is the short transient period of a capacitor charging. Okay, so that'll be one of the first circuits that we have a look at and analyse it this way, because we really know what the result is before we start. I'm just going to see that this gives that. So this is the underlying theory. We're not going to go very far with the underlying theory around transfer functions used in process control. All right. So typical examples include charging the capacitor, switch on, switch off, the current transient inductor circuit at switch on, switch off, the response of RLC circuits, what's called step, i.e. switch on, off, or ramp, where you've got a straight line, linear slope, so a voltage that is right and at a particular. This analysis, like I said, is around the process control. So, what the use of Laplace transforms do is they transform differential equation solution from one involving integration. Remember that last year, Kieran's got an integration. Yeah. But what this does is an alternate method, so it turns the solution from one that involves integration to one that involves a simpler algebraic manipulation. Pretty simple. Let's see, we'll find out. So the process involved, we transfer the circuit from a normal time domain into a new, what's called S domain, the Laplace transform. So we turn, and you'll see how this works when we do some examples, but we find an expression for the circuit, and then we if we express it in a new domain called, we then manipulate the Laplace transform algebraically so that it looks like one of the standard transforms in a table. And you'll see that table shortly. So it's a bit like your table of integrals and derivatives. And remember, they are mathematical opposites of each other, so we can go backwards and forwards. If we differentiate a function and then integrate it, we end up back where we started. Yeah? So what we do is we put this circuit into S domain, manipulate it until it looks like one of the functions we got in our table, which allows us to transfer it back. Yeah? I've not heard of the term algebraically. Algebraic. Once we've got an S domain function that looks like something in the table, we can then transfer it back to the time domain. We take the inverse Laplace transform. Alright? We're going to take a little look at how we find some of the simple Laplace transforms of functions, just to show you where they come from. But ultimately, all I'm going to be able to expect you to do is use the table like you did in differentiation. For some circuits, step 2, so this manipulation, algebraic manipulation, will involve the use of partial fractions and what's called perfect square techniques. these will either be revised or taught in this session so that you're able to do this. Yeah. So we've been a little bit less than a whole learn and outcomes worth on the working on the complex waveforms because we need a bit more time for this to teach the maths that you haven't already got. Okay. Had this course stayed on the college and we're still going to be teaching it going forward, I was going to put some of this maths in the module that you're doing now, so that you've at least seen it before you use it. That would have just been easy. But as they decided to stop the course, decided not to spend the time doing it. All right. Usually you guys have forgotten. So, what is a Laplace transform? We write the function and in brackets s. So the function in s space of a function. So this is in the s domain. A function s domain of a function in the time domain is defined. Yes, the integral to infinity of e test on started with in the first place et. Right? If we have a function that's got a constant multiplier, we just multiply that bit by that constant multiplier. Right? And if we have functions that are sums of one or more functions in a time domain, we integrate those separately and add them together. So if we've got two functions a and b, t plus b times gt, we do them both separately and add them together. Alright? I wouldn't get too worried about that, because other than showing you where the Laplace transforms come from in the table, some basic ones, I'm not going to expect you to do that. But I felt that was important that you actually, this is not a kind of blank canvas, you know where these things come from. Alright? If you're interested in knowing more about it, there's plenty in those fire engineer mathematics. I'm sure you're going to make a good bit of it. Alright? So we're going to have a look at a couple, just so you can see where some of the basic ones in the table come from. So, for this module, like I said, we'll not spend a long time determining the Laplace transforms, as the key interest is in using them. However, a couple of examples will help demonstrate how they are obtained. Okay, so if we take the Laplace transform for f of t equals 1, so very simple, single constant of 1. Yeah. So if we've got to integrate between 0 and 0 e to the minus st times 1 dt. Can anyone remember, have you got your sheets from last year? Laminated sheets? Here it has. So if I can find one for you, Callum, will be welcome. The process of integrating a variable to a power is that we add 1 to the index and divide by the limit. What do we end up with? Yeah. It's the multiplier here. So using the constant multiplier rule, f of s is equal to the integral k times the integral of with naught and infinity of e to the minus s t dot dt. Yeah. Now we've already done that. We've already solved that. That becomes 1 over s. The last one. So f of s is equal to k times 1 over s constant k. So if we got a different constant other than 1 in front of the e to the minus st, then we end up with just k. Now, on your next page, you'll see some example functions, what they are in the time domain, and what they are in the s domain. So here's our constant A for a step or a DC voltage applied. So we say we're going to do a step voltage of 10 volts, i.e. switch the circuit on to a constant 10 volt supply. In the S domain, that supply is that constant voltage 10 over x. A ramp is A times T. In the time domain, that will be A over S squared in the S domain. Exponential decay, so that's that decay QU of a capacitor discharging. A to the E minus BT in the time domain becomes A over S plus B in the S domain. Sine wave, A sine omega T in the S domain is A omega over S squared plus omega squared. So when you've got your expression for the complete circuit in the S domain, you're then trying to do mathematical or algebraic manipulation to make it look like one of these functions here so that you can transfer it back. Yeah? And we'll do example 2 of that. Alright, and once you're done a few examples, you'll be quite not that particularly difficult. Alright, with circuit you could get. So also you have a Laplace transform for the basic circuit components we're going to use. So the resistor, a resistor in S domain is R. So whatever, if it's 10 ohm resistor, that's just 10 in the S domain. Notice the unit ohms goes away. Inductor of L henries becomes L times S. No units anymore. And the capacitor, C farads, becomes 1 over Cs. Alright, so what we're going to do for the remainder of this session is look at getting an expression for the overall impedance of the circuit in S space. Then next time we'll start to look at how we apply the voltage to that and get a complete circuit to manipulate that. Alright? Because there's some work you can do on the impedance to get it in a form before that makes applying the voltage easy. Yeah? So you're going to need so don't lose it and don't not bring it, please. Okay, transforming the circuit impedance components into the S domain. The first part using Laplace transforms involves determining an expression for the total impedance of the circuit in the S domain. We'll consider a simple RL series circuit. So we've got R 10 ohms and L of 2 henries. Pretty big inductance, but you know, we'll deal with ones that are millihenries at some point. So that's in the time domain. From the table of transforms, I'm going to shorten that to LT. R in the time domain, say this, in time domain, ZT is equal to the resistance plus omega L J ohms. Yeah. Do you agree with that? 10. 2 omega J. Right. So what we're saying is, in a series circuit, we add the resistance and the capacitive inductive reactance together. Right. From the table of Laplace transforms that we have been given, R in the S domain is equal to R and L is equal to LS. This is L in the S domain. So that's what the table says right down the bottom, component values. Therefore, ZS is equal to R plus LS equals 10 plus 2 S. And you draw that in circuit form. Okay. No units now, no ohms. Everybody okay with that? Yeah. So that's a RL circuit, very simple. Right. So what we've got now is RC circuit. So Z in the time domain would be R plus 1 over omega C J ohms. In the time, complex numbers. Yep. From T table. R in the S domain is equal to R. C in the S domain is equal to 1 over CS. Therefore, Z in the S domain is equal to R plus 1 over CS equals 10 plus 1 over 2. So that is the expression for the impedance of a RC circuit in the S domain. Right? Callum? When you've done the conversion, the J's gone. Yeah. Right? Well, we've got J there. Just transfer to the S domain. Gets rid of all that. Yeah. All right. If you want to solve this problem in without doing the Laplace transform, you'd be into integration. You'd be into calculus. So this is an alternative method. Do you remember solving differential equations last year? Well, that's solving differential equations. Right, moving on then. Let's have a look at something that's going to turn out to be a little bit more tricky. So, we've got a resistance and an inductance in parallel. So I'm going to go straight to ZS now, because you're aware of what it's going to work in the S domain. How can I, in one go, write an expression for the impedance of that circuit? Bearing in mind RS is equal to phi and LS is equal to 0.2 times S. What's a formula for two impedances in parallel? Product over sum, yeah? So the product of these is 5 times, let's write it out in product, so we can go is equal to R times LS product over R plus LS. Yeah? So that's equal to 5 times 0.2 so 5 plus 0.2. We can simplify that. 5 times 0.2 is just S. Now, one further thing that will simplify here is that we want to try to get S in denominator we want to get S in the denominator on its own. So we just want S and not 0.2S. How could we do that? How can we make that 0.2S just S on its own? Yeah, so if we multiply through by 5, we have 5S on the top over 5 times 5 is 25 plus S. Yeah. Multiplied by 5. Not multiplied by S. Alright? No. No, what you've effectively done, Callum, let's just take that out a minute into its own. You've taken this expression, and what you've really done is you've taken S over 5 plus 0.2S, and you've multiplied it by 5 over 5, which effectively you've multiplied it by 1. So you haven't changed it. Yeah? So you've gone 5 times S on the top, and then 5 times 5 is 25, and 5 times 0.2 is S. So at any time, you can multiply a single side by 1 and not affect the whole thing. So you don't, if I multiply ZS by 5 over 5, what do I get? ZS multiplied by 1. Right? If you're multiplying by anything other than 1, then yes, you've got both sides. Have done it to both sides, but yeah. Alright? You happy with that explanation? Yeah. Multiply by through by 5. Effectively what you're doing is multiplying by 5 over 5s, because we've done it to the top and bottom. Alright? Right. Let's put one up for you to have a go at. thought that. Another example. Remember, you've got to be able to get the knack of these guys, so come on, let's concentrate. Another example. Resistor and capacitor in parallel. So RS is 10, CS is 1 over 4. That's R in the S domain. Take the ohms away and just use the number. Yeah. And C in the S domain is 1 over 4S in this case. Yeah. So we're going to do ZS is equal to RS plus, oh hang on, RS times CS over RS plus CS. So that is top line of 10 times 1 over 4S divided by 10 plus 1 over 4S. Yeah. Right. Now, 10 times 1 over 4S is equal to 10 over 4S. And we divide that by 10 plus 1 over 4S. Now, we could write this denominator as a fraction of a 1. Yeah. You've got a fraction now, top and bottom. Yeah. How do we divide two fractions? We've gone back a long way now, first year maths. Turn bottom fraction upside down and multiply. If we've got A of a B, of a B of a C of a D, this is the algebra rules, and that's equal to A of a B times D of a C. We turn that bottom fraction upside down and multiply. So in the case of our Laplace transform, it's equal to 10 over 4S times 1 over 10 plus 1 over 4S. Follow? If we then do multiply that out, 10 times 1 is 10. Over 4S times 10 is 40S. plus 4s times 1 over 4s is equal to 4s divided by 4s is 1. What do I need to do to get s as a single s on its own? What have I got to do to make that expression just s? Multiply by 40. 40 times 40s is? So 10 over 40 is 0.25, a quarter. And that becomes s. Fives, not s's. All right? Yep. Okay. Right. So that's we've now done series RL, series RC, parallel RL, parallel RC. All right. Let's have a look at RLC. All right. So read that up a bit. First of all, the basic quantities RS is equal to 3, LS is equal to 1.2, and CS is equal to 1 over 0.5 S. Right? So we can write this, the impedance in the S domain is equal to, going to be RS plus L in the S domain plus C in the S domain, which is 3 plus 1.2 S plus 1 over 0.5 S. All right. How can I make that so that it's simpler if at this stage if that fraction is just 1 over a constant over s. So just dealing with that fraction, what can I multiply it by? So that's just s on its own on the bottom. Yep. So we can say that's equal to, you don't have to do that to these, because we're only multiplying that bit by 1. Yeah, because we're multiplying top and bottom of, let's just draw that. We're going to take that bit only and multiply by 0.5. Sorry, we've got to multiply by 2, haven't we? 2 over 2. You don't have to do that to these because you're only multiplying them by 1 anyway. Yeah, so plus 2 over s. And this is z in the s domain is equal to that. Okay. Now, what we need now, we need all of the right-hand side to have the same denominator. So this has got a denominator of s. Yeah. So we want these also to have a denominator of s. So if I multiply this and this by what to get it as something over s? So what we want is z of s is equal to, hang on, let's start to write this out, 3 plus 1.2s plus 2. That one's over s. I want this one to be over s. So if I multiply the bottom by s, what have I got to do at the top? So 1.2s times s is s 1.2s squared. I want this to be over s. So what do I multiply that by? S. Yeah. So we can write that out in all in one form with one common denominator, 3s plus 1.2 s squared plus 2 all over s. Yeah. So that's RLC. Yeah. There's another RLC in your notes. Have a go at that one.